Welcome back to the second of a four-part series covering kernels. In this video, we'll discuss how we can get around the curse of dimensionality we experience using basis functions with something called the dual representation. Go here for a description of this notation. The dual form comes from linear algebra. In order to make sure that we're all on the same page, let's go over a little reminder of a few important concepts. Let's assume A is a matrix in a real numbered space n by m, where n is the number of samples and m is the number of dimensions. The row space, or calligraphic A, is the set of all possible linear combinations of its rows. In other words, calligraphic A is the span of the rows of A. The null space of A is the orthogonal complement of calligraphic A, and is also known as the kernel of A. This gives us the useful property, by definition of the null space being orthogonal, that every element in the null space times A is equal to 0. Okay, what does that mean? Well, if we look to the right, let's assume A looks like the following. The row space of A only covers the x and the y dimensions. That means that the kernel of A, or the null space of A, is the z dimension. Okay. What does that mean exactly? Well, let's assume that the calligraphic A is a subspace of Rn. That means that the union of calligraphic A and the kernel, or null space of A, gives us back Rn. So, we can use something called the orthogonal decomposition to uniquely write any vector in Rn as the vector addition of a vector from the row space with a vector from the null space. Here we denote the vector in the row space with a hat, and z is the vector from the null space. This should make intuitive sense to you. Okay, now that we're on the same page regarding terminology, let's look at what it means for dealing with our problem of a dimensionality. So, let's set x to be all of the training points that we currently have. Now, we know from earlier lectures that we can write our linear model as y of x equals w transpose x. Using what we said about the orthogonal decomposition from the last slide, we can rewrite our weight vector w as the vector addition of w hat and z, where w hat is the row space of x and z is the null space of x. That means that we can rewrite our prediction equation as follows. Y of x equals w hat plus z transpose x, which is equal to w hat transpose x plus z transpose x. And since z transpose x is 0, this means that w hat transpose of x is equal to w transpose of x. That means that w is in the span of x. This means that we know that the weight vector w is in the row space of x. What does that mean? Think about it. Say it out loud to yourself. What does that mean for w? Where's w coming from? What is it tied to? That means that the weight vector w is a linear combination of the training samples of x. So we can rewrite w as the following, where the vector A is known as the dual parameters. And like we've already seen in this semester, we can easily substitute a linear function of x for a nonlinear function of x using the basis functions without changing any of the conclusions that we've just made. But the big thing is that this discovery gives us is that now the number of dual parameters is the same as the number of training samples. It isn't tied to the number of basis functions anymore. Remember previously we needed one weight parameter for each basis function? We don't need that anymore. So, if we substitute our new form of w back into our y of x prediction function, we get a new form where k is the kernel function of phi. This means our gram matrix becomes a matrix of our kernel. It's pretty straightforward then to see how this changes our prediction function. So we substitute in this formulation of the dual parameter times the kernel summed over all training points, and that gives us the sum of all the training points over m by n kernel, which then becomes the vector of our dual parameters multiplied by the kernel matrix, our gram matrix. And that gives us our predictions. If you remember, our previous formulation of this was simply W transpose phi of x, where phi of x was the decision matrix. By comparing the dual representation on the right with the primal representation on the left, we see that the objective function has exactly the same form. Thus, the solution of the dual representation is given by the Moore-Penrose pseudo-inverse of the gram matrix of K. However, here the number of parameters, and therefore the complexity of solving the equation system, is determined by the number of training samples, and is independent of the number of basis functions. As shown on the previous slide, the predictions can be calculated directly from the dual representation, without the need for explicitly calculating the weight vector. As I already mentioned, this means that the dual form is only dependent on the number of training samples and not on the number of basis functions. If you think back to our example of Gaussian RBFs, that means that in this form, if we had 21 training samples, we would only have a big O of 21 raised to the third power, instead of a big O of 16 raised to the 45 power. That's quite the cost savings. So let's take a peek at what this would look like using our example from before. Our definition of the basis function is the same. We calculate the kernel, and we expand it out into this formulation. But in our linear regression view, it still looks very nice, and you can see that we're influenced by n, the number of training points, not by m, the number of basis functions. Just for another example of a kernel related to something we've already seen before in primal formulation, let's look at the polynomial basis. The dth order polynomial basis induces a d-dimensional feature space. The kernel is defined as the scalar product in feature space. Thus, we must sum over the products of all features. Now, this is a geometric series, and by applying the geometric summation formulation from calculus, we can see that we can calculate the value of the kernel without actually evaluating the sum. Thus, even for large values of d, the calculation remains feasible, while explicitly calculating the features would require too much time and memory. The square gram matrix contains as many rows and columns as there are training samples. Each entry corresponds to the value of the kernel of the two training samples. Therefore, we just have to substitute x and y for x sub n and x to the n and x to the m to get the corresponding entries of the gram matrix. So now you can see how powerful these kernels can be. Up next, we're going to learn more about the properties of kernels in general so that we can better understand how to use and how to create them.